everyone, now we will discuss on the topic air pollution control part 2. In this class, we will be focusing on electrostatic precipitator and fabric filter. Now, we will see what electrostatic precipitators are. As you know, the particles are normally having negative charge. So, if we can create some electrical field through which the particle laden gas is moving, so in that case the negatively charged surface of the particles will help to move it towards the positively charged collectors. So, the particles can be collected. So, ESP is basically used to remove the particulates from gas stream by this mechanism. Now, let us see this figure. So, here we have shown these two plates. So, these two plates are collecting electrode plate, and these are another electrode. So, this you see, this is connected to negative sides and these are two positive sides. So, these are the anode and these are the cathodes. Due to the use of these two types of electrode, there will be some current into the circuit, or if we connect some current to this circuit. So, one electric field will be generated in between these two plates, and now we are sending the gas. So, gas inlet will be having the particulates. So, these particulates will be having some say negative charge at its surface. So, these are positively charged, these two plates are. So, it will be moving towards this collection and it will be collected. So, once these negatively charged particles is moving and getting arrested by this, so it will fall. Similarly, it can move, any particle can move these directions also. So, then that will also be fall. So, this is the mechanism of the collection of the particles. Now, this is for parallel plate precipitator. There may be different geometry. This can be a wire and pipe precipitator. So, here say this is our pipe, a tubular pipe. So, here we are, it is positively charged. So, this surface will collect the particles and inside we have put one wire and there is some electrode, that is anode, and this is our cathode. If we supply electricity, then there will be some electric field and then particles which are negatively charged, those will be moving towards the surface and will be collected. So, the same mechanism here also. Now, if we see this particle, so there are basically two types of forces, one is your gravitational forces and another is this electrical forces which we are getting. So, parallel plate precipitator and wire and pipe precipitator, in both cases the same similar type of phenomena we will be getting, only the difference in the geometry. So, then how can we define the collection efficiency? In such case, the collection efficiency is equal to 1 minus exponential minus Vpm AC by Q, where Vpm is drift velocity and AC is the collector surface area and Q is the volumetric flow rate. Now, you see that Q is the volumetric flow rate into L by V is equal to V. So, V is equal to what? The volume of the precipitator. So, volume of the precipitator, if I want to calculate, so that will be Q into L by V, where L is the length of the precipitator and V is the gas velocity. If we see this figure, V is the gas velocity. So, length is the precipitator and then we will be having the V gas velocity. So, Q into L by V equal to V, that we will get. Now, by using this expression, by replacing this Q, that is means the volumetric gas velocity, volumetric gas flow rate, we may not be able to measure every time. So, we can convert it in terms of some known parameter, that is volume of the precipitator and length of the precipitator. These are the your design parameter of this, okay, the geometry of this precipitator. So, it is easy to calculate and use the formula for computation purpose. So, then efficiency is equal to 1 minus exponential minus V p m A c. Now, Q is replaced by this relationship. So, V into V, small v into capital V, and in the numerator we are getting A c into L. Now, A c by V, this is another term is coming, A c by V. What is A c by V? That is equal to surface area by volume of the collector. For tubular type precipitator, A c by V equal to 4 by d c, where d c is the diameter of the collector, and for plate type precipitator, A c by V is equal to 2 by S, where S is the distance between two plates. Say we have two plates here. So, this plate and this plate both will be collecting. So, L into S, L into H. So, L H is the S. So, 2 into A into A. So, 2 A c, and volume will be that A square into S, the distance between two plate. So, we will be having say this is one plate and this is another plate. So, in between the distance is equal to S. So, if it has L and this W is our width. So, the area we are getting W into L and 2 we have. So, that is equal to 2 and divided by volume is equal to W into L into this distance S. So, that is equal to W W L L cancel. So, 2 by S we will be getting here. So, plate type S equal to distance between two plates and A c by V equal to 2 S. So, by putting this parameter, now we can calculate the value of efficiency for the collection. But this drift velocity, the drift velocity will be depending on many factors. So, that will be depending on the particle size, gas viscosity, particle charge, okay, and another constant, that is Cunningham correlation factor. So, how this is? So, V p m is equal to Q p E c c divided by 3 pi mu g d p, okay, where this E c is nothing but the electric field strength and c is the Cunningham correlation factor and mu g gas viscosity and d p is the particle size. Okay. So, that way you can calculate the V p m. Now, this c is Cunningham correlation factor, that also depends upon the nature of the gas. Okay. So, this can be calculated as c equal to 1 plus 2 lambda by d p into 1.257 plus 0.4 e to the power minus 0.55 d p by lambda. So, this lambda is the mean free path of gas molecules. So, that is why depending upon the type of gas, this c value will depend. So, it is very clear that efficiency value depends upon many factors including the nature of the gas. Now, let us see one numerical problem. A MSW based power plant is emitting 45,000 meter cube per hour flue gas. It is proposed to install an ESP with a collection efficiency of 96.8%. Calculate the total area of the collection electrodes. If the collection efficiency is 99.5%, how much additional collection electrode area would be needed? Drift velocity of the particles has been determined experimentally at 0.13 meter per second. So, drift velocity is already given. So, we do not need to calculate it from other parameters. Okay. So, here the volumetric flow rate is given, that is 45,000 meter cube per hour. So, we will convert it into meter cube per second. So, 45,000 divided by 3600, so it is coming 12.5 meter cube per second, and we have the expression for calculating efficiency, that is efficiency is equal to 1 minus e to the power minus V p m A c by q. So, for the first case we have this efficiency is equal to, we have 96.8%. So, we have 0.968, that is equal to 1 minus e to the power minus Vpm, it is given 0.13. So, this AC we need to calculate, and Q is we have calculated, that is 12.5 meter cube per second. So, from this expression by rearranging we will get the value of AC is equal to 330.96 meter square. So, 330.96 meter square. So, this is for the first case. In the second case, our efficiency is more. So, certainly the area requirement will be different. Okay. More area is required because collection efficiency is more. So, the same expressions we will be using. So, in this case the efficiency is equal to 99.5%. So, that is equal to 1 minus e to the power minus 0.13 into AC divided by 12.5. So, same expressions we will be getting, and by solving this equation we are getting AC equal to 509.45 meter square. So, more area is required in this case. So, what is the requirement of more area, that is 409.45 minus 330.96. So, that is equal to 178.49 meter square. So, that way we can find out the area which has to be increased to increase the efficiency, collection efficiency from 96.8% to 99.5%. Okay, now we will discuss the fabric filters. So, you see this figure shows us the operation of fabric filters. So, here this is our dirty gas, it is coming in, and there are number of, we can say stand, we can see these are the cages, and this cage is covered by the fabrics or the bags. Okay. So, then this particulate matter laden gas is coming here, that is the dirty gas, and it will be passing through the fabrics. Basically there is one blower at the top. So, some suction is there. So, which gas is coming, it will be forced to go through it, through the pores of it. Okay. There may be two types of arrangement, you know. So, we can have the cage like this. So, this cage maybe air pass through this, and the cloth will be at the outside of it, and air may pass again through it, or another type of arrangement may also be possible, that is from this the gas is going. So, that way also it is possible. So, here if gas gets entry here, so it will be going out from this, and that will be going out. So, that is due to the blower which is working at the top of this. So, that way the fabric filters work. So, a fabric filter unit consists of one or more isolated compartments containing rows of fabric bags, that is shown here in this figure, in the form of round, flat or shape tubes or pleated cartridges. So, different types of arrangement can be used in this case, and particle laden gas passes up along the surface. So, gas is going along the surface of the bags when radially through the fabric, then particles are retained on the upstream face of the bags, and the cleaned gas stream is vented to the atmosphere, just which we have discussed. The filter is operated cyclically, alternating between relatively long periods of filtering and short periods of cleaning. So, there is some off time and on time, long on time and small off time that is there. During cleaning, dust that has accumulated on the bags is removed from the fabric surface and deposited in a hopper for subsequent disposal. So, particles are deposited on the surface of it, then when you are cleaning, these dust are being collected, it falls and then it is collected. So, this is the mechanism of the fabric filter, and the type of cleaning may be either shaker cleaning or reverse air or pulse jet cleaning, and direction of gas flow may be from inside the bag towards the outside or the vice versa, just we have discussed, and suction or pressure, both arrangements are there. So, suctions are there when it is going for cleaning and when it is working in normal operation, and during cleaning the pressure can be applied. So, the salient features of these fabric filters are it is highly efficient, 99.9% or more than that efficiency is possible. It can be suitable for smaller particles also, that particle size greater than 0.01 to 1 micron, where the in case of settling we had seen that gravity settler it is more than 50 micron, but here it is 0.01 to 1 micron particle size can be separated, and low pressure drop 5 to 20 inches of water. It has some disadvantage also, like it cannot operate in moist environment, and it is relatively larger volume and expensive bags, like the fabrics are expensive, and it is competitive with electrostatic precipitator, and temperature normally below 285 degree centigrade. And when we use the fabrics, those fabrics or maybe woven fabric, or it is felt cloth made of cotton, nylon, polyester, fiberglass, asbestos, etc. And the most important design parameter is air or gas to cloth ratio, air to cloth ratio or gas to cloth ratio. And the major operating feature of fabric filters that distinguishes them from other gas filters like say HEPA filter. So, is the ability to renew the filtering surface periodically by cleaning, that is it can be operated continuously, but HEPA and other type of filters may be working for certain time and then it has to be discarded. You see here this is one HEPA filter is shown. So, high efficiency particulate air, that is HEPA, high efficiency particulate air filter. Media is usually made with borosilicate microfibers within diameters of 2 to 500 nanometer, and both in case of this type of filters or fabric filters or HEPA filters or bag filters. So, we have fibers, those are responsible for the separation of the particles. So, the characteristics of the filtration process lead to these fabric flow related capturing mechanisms known as the inertial impaction and then interceptions and diffusion. So, then three major types of mechanisms are there which are responsible for the collection of the particles in this type of device, and now we will see those different types of mechanisms. Here this figure shows us your inertial impaction, and this is your diffusion, this one, and direct interception. So, direct interceptions here inertial interception, you see the in case of direct interceptions the particles is coming here, okay. Though, but in case of inertial impaction the separation through collision and adherence with fibers. So, collision and adherence, and here it is adherence and we are seeing, and in case of diffusion the density or concentration gradient will also responsible for the movement of the particle. When it is outside then it is going to the inside, but here the particle is already in the inside, okay. So, that way the mechanism is different. So, the separation through inertial impaction we can calculate the efficiency, that is efficiency impaction is equal to phi c and phi a, that is adherence factor phi a and collision factor phi c. So, theta c theta a, and these are the factor of fiber Reynolds number and eta. So, it is the Stokes or inertial impaction parameter, and this is your function of this. What are those exact expression? Exact expressions are like this. So, eta through impaction efficiency for the collection through impaction, that is equal to this expression we can calculate, where we see that these are related with dP particle diameter and df fiber diameter and eta and ku. So, ku and ff also. So, ff is fibers solid fraction and ku is Kowabarra hydrodynamic factor. So, these are we are getting, and ku is equal to ff minus 3 by 4 minus ff square by 4 minus half into ln f. So, these are the different expressions which are available to calculate the value of efficiency due to impaction. Now, for direct interception, the formula we can use, that is equal to eta interception, that is equal to 1 plus dp by df minus 1 by 1 plus dp by df, that is for potential flow, laminar flow, and for viscous flow we are getting, that is efficiency for interception is equal to 1, this expressions which is given here. So, again this is also dependent on dp and df. Okay. So, mostly 99.9% of collection takes place through the combination of these two methods or mechanisms, and diffusion also when the particle size is very small, that submicron particle. So, that will also be diffused as I shown in the previous slide, that is from the outer to inner side. So, that diffusional motion of the particles can be affected by their collisions with gas molecules. Thus, particles do not normally follow the streamlines surrounding the fiber, and efficiency for diffusion can be calculated by these expressions, where 0.775 into CDF REF by this is REF that is fiber Reynolds number by 2 to the power 0.4 into Peclet number to the power minus 0.6. Okay, so, CDF is drag coefficient for the fiber and P is equal to Peclet number. So, for combined efficiency, that will be 1 minus eta impaction into 1 minus eta interceptions into 1 minus eta diffusion, and this is for one fabrics. So, one fiber, this will be the combined efficiency, but if we have number of fibers, then overall efficiency we will be having 1 minus Cl by Co, that is the what concentration of particulates in the inlet and what is in the outlet. So, that will be used to calculate the actual efficiency for the overall case. So, 1 minus Cl by Co, and Cl is the initial concentration of the particles and Co final concentration of the particles, and Co is the initial concentration of the particles. So, this will be 1 minus exponential minus eta f 4 by pi d f into ff by 1 minus ff into L, where eta f is the individual fiber efficiency, L is the length in gas flow direction. So, in addition to the above three collection mechanisms, electrostatic forces between particles and fibers increase the collection efficiency, and electrostatic charge in filter fabric is due to friction between gas and fabrics as well as that between particles and fabric at high gas velocities, that is 1.5 to 2 meter per second. Now, we will see different types of filters and fabrics which are used in this type of filter. So, here you see the fibers are either woven or it is felted fiber. So, this it is very clear that in case of woven filter, the volume of this fiber is much more than in case of felted filter. Okay. So, the packing density is one parameter through which we can quantify the quality of these type of filters. So, that packing and packing density or solidity, that is defined as the fiber volume by total volume or 1 minus porosity. So, for felted filter this is less than 0.1, wherever for woven filter this is around 0.3. So, woven filters are made of yarn with a definite repetitive pattern, and felted filters are composed of randomly placed fibers compressed into a mat and attached to loosely woven backing material. Membrane filter is a special treatment where a thin porous membrane expanded polyfluorocarbon is bonded to the screen or support fabric. So, these are the different types of fabrics or patterns or processes which are used, and now we can see the performance of different types of fabrics which have been used in real field. So, different fibers, that is a cotton, polyamide, polyester, tetrafluoroethylene, and if we see that their relative strength and then maximum usable temperature and relative resistance to attack by acid, base and organic solvent also provided, and other properties are also provided. So, for cotton you see relative strength is strong, but maximum usable temperature 80 degree centigrade, and for acid it is relative resistance is poor, for base medium and organic solvent it is good, and other properties it is of low cost. Similarly, for nylon, so relative strength is strong. So, here maximum temperature is 100 degree centigrade and acid resistance is medium, base is good and organic solvent is good, and easy to clean, excellent resistance to abrasion, it is easy to clean and it has excellent resistance to abrasion. And your polyester, again it is strong strength 135 degree centigrade it can be used, and it has good acid resistance, medium base resistance and good organic solvent resistance, and easy to clean also. So, tetrafluoroethylene, it is also relative strength your medium and it can be applied up to 260 degree centigrade, and it is good acid resistance, good base resistance and good organic solvent resistance, but this is expensive. Other are glass and Nomex nylon and wool. So, you see a glass is strong relative strength, maximum usable temperature 280 degree centigrade, relative acid strength medium, base strength medium and organic solvent strength also good, and it is poor resistance to abrasion. And Nomex nylon, it is strong relative strength and maximum usable temperature 230 degree centigrade, it is good acid strength, medium base strength and acid resistance, medium base resistance and good organic solvent resistance, and this is poor resistance to moisture. And for wool, it is medium relative strength, maximum usable temperature 95 degree centigrade and acid resistance medium, base resistance poor and organic solvent resistance good, but fair resistance to abrasion it has. So, these are the different fibers which can be used, and depending upon our need we can select any one for our application. Now, we will discuss on the cleaning aspect, how the fibers or fabrics can be cleaned when say we are attaining certain pressure drop, then we need to clean it. So, there are basically three types of cleaning methods we have discussed. One is your shaking, then another is your reverse air and another is your impulse air. So, now here you see we have a bag. So, particles are attached to the surface, outer surface of it. Then if we can create some disturbances, so that is using ultrasonic or through the sonication, so then there will be disturbances and it will be sucked and the deposited particles will fall. So, that is one way. Other way, we can make some arrangement for oscillations, like say this type of oscillations. If we make some oscillation, so there will be the cloth will disturb and the particles which are deposited on it will settle. Or we can arrange some sacking, like say this is vertical direction, we can put some mechanical arrangement. So, it will be sacked and the cage will be deformed to some extent, and in that case the particles which are associated at the outer side of the fibers or the fabrics will be separated. So, this is the Shaker cleaning mechanism, and here frequency several cycles per second and motion type simple, harmonic or sinusoidal, and peak acceleration 1 to 10 gravity, and then amplitude fraction to a few inches, and then mode upstream, it is done upstream, and duration 10 to 100 cycles, 30 second to few minutes, and common bag diameter is 5, 8 and 12 inch. And here this is your reverse air. So, here in normal conditions, so if air goes through this, in the reverse air the air will go into opposite direction. So, this is the mechanism, and in that case also it will be we will be having the particles which are deposited, that will be opposite flow it is getting. So, that will be settled. So, this is one reverse air mechanism through which this can be cleaning can be done, and frequency here clean a compartment at a time, sequencing compartment after another, continuous or initiated by a maximum pressure drop switch. And motion type, it is gentle collapse of bag upon deflation, slowly repressurize a compartment after completion of a bag flush, and bag diameter 8 to 10 inch, length 20 to 30 feet, and bag tension 50 to 75 pound, and mode upstream, duration 1 to 2 minutes including wave opening, including valve opening, closing, dust settling period, reverse air flow itself normally 10 to 30 second, and common bag diameter 5, 8 and 12 inch. And you see here the pulse jet. So, pulse jet we are providing air, okay, with a very small duration inside the bag. So, there is some on off time, there is on off controller. So, when there is some instrumental air, so that instrumental air will give some air inside this bag. So, this through this air nozzle, and this will be air bubble will create, and it will disturb the particles which are associated with the fibers or the fabrics from its outer surface. So, the particles will fall. So, this is the mechanism. So, here also has some characteristics like the frequency, a row of bag at a time sequenced one row after another can sequence such that no adjacent row clean one after another. Initiations of cleaning can be triggered by maximum pressure drop switch or may be continuous, and motion, shock wave passes down bag, bag distance from cage momentarily, and mode on stream in difficult to clean applications such as coal fired boilers, off stream compartment cleaning, duration compressed air, that is 100 psi, pulse duration 0.1 second, bag row effectively offline, and then bag dia 5 to 6 inch. So, these are the different methods which are used for the cleaning of the bag. Out of these, this one, the last one, the pulse jet is used in many cases in the industry, and the last we will discuss the air or gas to cloth ratio. So, the air to cloth ratio of a filter is the amount of air flowing through each square foot of filter media per minute. So, the air to cloth ratio is typically between 1.5 and 3.5 meters per minute, mainly depending on the concentration of dust loading. This meter you are know, this meter means meter cube per meter square, that is why it is meter. Okay. So, then we are getting the V is equal to Q by A. So, filtration velocity, or you know this is the average velocity. Okay. So, this table gives us some data on air to cloth ratio for different types of cloths. You see different types of industries where these bag filters are used, and different types of cleaning purpose, cleaning method. So, reverse air, pulse jet and mechanical shaker. So, in these cases air to cloth ratio is also provided. So, when we will be in need to design a particular filter unit or say fabric filter or bag filter for a specific application, all those information will help us to decide its size and to decide its fabric, to decide its operating conditions like air to cloth ratio, etc. So, up to this in this class, thank you very much for your patience.